My goal for this video is to help you understand the notations for single, double, and triple integrals, and these right here are extremely important because they will help you to set out a strong foundation when you learn multivariable calculus. So make sure you understand all this, and here we go. First, notice that I have nothing between. Technically, it's just a 1. You don't have to write down the 1. And if you look at the first one right here, we have a single integral and we have dx. This is in the one-dimensional case. When we have dx, that means we're on the x-axis. And sometimes you see some numbers from here to here. Well, that means that we're integrating over an interval. So you can put a capital I is equal to, like say, the interval going from 1 to 7 or something like that. But nobody really does it. Here is an example. If you look at the integral, let me just, instead of 1 to 7, put down a to b, and then dx. Now, what does this mean? Dx, we are on the x-axis. And the dx really means just a small piece of the x-axis, a small change in x. So it's something like this. And the thing about integration as a super version of addition, what we are doing is we're adding up all these dx's from a to b. And after we have done that, what are we going to get? It's not just going to give us the length from a to b. Yeah, and the answer for that is just b minus a, but I just want to write down the key is once we have done that, we are going to get a length once we compute this single integral. Now you might be wondering, don't we use single integrals to help us find area? True that. That's when you have a function here. Well, first, if you have a 1, you can just build up a 1 like this. And the area of that rectangle is also b minus a. That's not fun, right? When the height is 1. But if you have a different function such as x squared, then you are going to graph that, then you are going to get the area under the curve. But here, if you just have this, it's just the length. Once you understand this, later on it's going to be much easier for you to understand the notations for line integrals. Now, moving on to the double integral notation. dA, of course, we're talking about areas, and here we are talking about the two-dimensional case. Sometimes you see functions, and a number, but most likely you will just see like a capital R or capital D or whatever notation they are to use. The key is we will be integrating over a region. So if you just finish this integral, you are going to get an area. And if you take a look at this example, integral a, b, c, d, and then dx on the xy plane, we will have dx, dy. Could it be dy dx? Sure thing, but yeah, let me just put on dx, dy here. What does this mean? Pretty much the same idea, but just the extension for this. On the x-axis, we are going from a to b, adding up all the small dx's. And then on the y-axis, we will have a bunch of the dy, and we are going from c to d. Now, if you multiply dx and dy, you're going to get a small piece of the rectangle like this. And that's like a differential area. It's like this. It's like the extension of the little dx. Now, when we do double integrals, meaning that we'll just be integrating all these pieces, and we are going to be getting the area of this big rectangle. And yes, sometimes if you have function and a different function here, you're just going to get like a curvy side, so you have different shapes. But at the end, whatever you get, keep in mind, you'll be ending up with an area. Now, pretty much the same question like earlier. Don't we use double integrals to help us find volumes? True that. Firstly, whatever this answer is, which is b minus a times c minus d, that answer could be interpreted as a volume as well, because imagine if you have a 1, it's like you have a bottom part right here, a rectangle, and then the height is 1, and the volume of that rectangular box is the same thing as the area of this rectangle numerically. And if you have a different function here, multivariable functions such as x squared, y, blah, blah, blah. What you are doing is, once you set this up, this is your base. And then look at whatever that function is. And then you're going to build up the function like this. And then it may be curvy. And then you're going to find out the volume of that solid. Really cool stuff, but very difficult as well. And I will tell you though, before we move on to the next one, in order for us to do triple integrals really well, make sure you master this right here. Especially change of the order of dy, dx, dx, dy, all that stuff. And sometimes maybe polar. Finally, 3 dimension. Of course, this right here, we'll be talking about integrating over a solid. And again, you may see some different notations. Capital B for a rectangular box or a capital E, etc. But what we're doing is whatever that represents is going to be, whatever they write, it represents a solid. Okay, you know what's coming. Integral, 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 A, B, C, D, E, F. Okay, I'll stop. Now, once we're in the space, we have X, Y, Z. dV is just dx, dy, dc. Of course, up to rearrangement, but that will be a different story. What does this mean? I'm going to give you my best picture. Here. X, Y, Z, right? Usually X and Y, and then Z. In this case, the Z will be coming off from the board because we use the right-hand rule. X-axis, Y-axis, and then Z-axis. The positive directions. However, when you want to draw a nice 3D picture, I think it's more natural if you do like this. Put down the positive x-axis here, and then the positive y-axis in this direction, and then positive z-axis in this direction. Now, this is pretty hard to draw, but I will try my best. In the x world, we are going from A to B, so I'm looking at this. Let's say here is my A, and here is my B. And notice that my little thing right here is parallel to my y-axis. Anyways, that's that. And then of course we still have the dx, but let me not label it anymore because it gets too crazy. Now on the y-axis, let's say we have this C up to D. And then finally on Z, we have E to F. So let's say here is E, and then here is F. And of course, here is the dy, and here is dz. Now, how are we going to draw the rectangular box in this case? In my opinion, I would suggest you to do this. Go to the xy plane first, and then draw kind of like the shadow. Right here, just kind of start from A and C intersection like this, and then you draw a parallel to that, and then you draw a parallel to this, and then you draw a parallel to that. Technically, it's a rectangle, but I'm trying to make the picture 3-dimensional. But this is just on like the shadow, right? It's not actually the answer. Because our rectangular box is not on the xy plane. It starts at when z is equal to e. So it starts right here. So what are we going to do though? I'm going to do like this, and then just try your best, because if you look at it like this and then goes like that, right? So it will be something like this. And then just kind of try to connect the parts. So this distance is meant to be E. And then F is right here, but you go to the front a little bit, like so. And then finally just kind of connect it. Like this. And you're not supposed to see this right here, so you can erase it to make it a little bit more 3-dimensional looking. Now, finally, dx, dy, dz. When you multiply all three together, you're just going to get a small rectangular box like this. And that's like the extension of that. But anyways, what we're doing is we're triple integrating like this, right? We're just integrating all these little volumes, and at the end, you're going to get the volume of this blue box. The key is, after you finish this integral, you will get a volume. And again, sometimes you may see some functions here, 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 and then on the very outside, it must be always number, number. If you have functions, that means you just have like different shapes, different curves, different surface on the side, etc. It gets pretty complicated. Now, the final question is that when we have a triple integral, we get a volume already. What if sometimes we have a function here? Then what are we going to interpret that as? Fourth dimension? Not really. Sometimes if you have like a super crazy triple integral with a function in between, usually we'll say something like that function is like a density function. Just imagine this blue box here. Density might not be different throughout the box, right? Maybe this corner is heavier because it's made of gold, and this little corner is much lighter because it's made of plastic or something like that. And then if you integrate all that, you're just going to find out how much this box actually weighs, because you have the volume and then times the different densities throughout the box. Just like that. So hopefully this right here helps. I'm going to talk more about this notation because it's extremely useful. I want to talk about centroid. What's that, right? That's it.